Welcome to the IBS Center for Climate Physics, ICCP, here at Busan National University. I'm Axel Timmermann, the director of ICCP, and I would like to invite you today to join me on a small tour through our center. Let's begin with our logo. It shows 5 key Earth system components that our scientists study: the atmosphere, the hydrosphere, which includes oceans, lakes and rivers, the biosphere, which includes vegetation and marine ecosystems, the cryosphere, glaciers, ice sheets and sea ice, and the anthroposphere, characterizing the human footprint on these systems. The integrative nature of our center is symbolized by the camera aperture design. Before we talk about our scientific endeavors, let me say a few words about our history, mission, scientific goals and our structure. I launched the ICCP in 2017. We have now 34 researchers, including 5 professors, 15 PhD students and 8 support team members. Members from our center come from 10 different countries: South Korea, Germany, India, China, Pakistan, the United States, Madagascar, Kenya, Belgium and the Netherlands. We occupy the 10th and 11th floor of the building on the left, located on the campus of Busan National University. The views from our offices into the valley and surrounding mountains are absolutely stunning. We are part of the Institute for Basic Science, short IBS, South Korea's leading organization for basic science, funded by the Ministry for Science and ICT. The motto of IBS is making discoveries for humanity and society. The science conducted in our center helps to improve lives and livelihoods of people in South Korea and around the world, but more on this later. In our center, which is one of 34 centers across South Korea, we strive to improve our understanding of natural climate variability and man-made climate change. Using Earth system computer models, we develop new methods to simulate the impact of various forcings on our Earth system. More specifically, we address how future anthropogenic effects will influence the atmosphere, ocean, ice sheets, sea level, planetary life and regional processes. Our approach combines theory, supercomputer model simulations, fieldwork as well as lab work in a unique and integrative way, allowing us to address fundamental questions in Earth system dynamics and human evolution. This slide encapsulates our research philosophy, past to future. What you see is the evolution of global mean surface temperatures over the last 3 million years as simulated by our coupled general circulation climate model. On the left, we see the warm temperatures of the Pliocene 3 million years ago, the gradual cooling moving to the right during the so-called Pleistocene epoch, and the onset of astronomically forced major glacial interglacial cycles around 1 million years ago. This unique computer model simulation conducted on our supercomputer Aleph overlaps with some key stages in the evolution of our genus Homo and the emergence of Homo sapiens. This allows us to link for the first time climate, vegetation changes with key stages in human evolution and migration. Starting from this long paleoclimate simulation, we then conduct additional simulations into the future using greenhouse gas forcing scenarios. With this approach, we can first test the climate model against paleoclimate data to have more confidence in our future projections of climate. I would like to give you a brief introduction into the main research questions in our center. Professor Juni Lee and me, we work on various questions of Earth system sensitivity and predictability. Professor Kyung-Ja Ha's work focuses on recent and future changes in rainfall patterns and monsoon systems. Professor Christian Franzke and me address issues pertaining to the past, present and future responses of human systems to changes in climate. And Professor Wonson Park and Dr. Eunyoung Kwon study how climate change influences the ocean and marine biogeochemistry, respectively. One of the main research tools in our center is the Aleph supercomputer, a Cray XC50 liquid cooling, which can complete 1.5 quadrillion floating point operations per second. It's one of South Korea's fastest supercomputers, about 10,000 times faster than a normal laptop computer, and our parallel storage devices and data archiving system can store large amounts of data comparable to about 53,000 hard disks. We run climate model simulations on this computer that cover Earth's history of the past few million years. We compute the response of the major ice sheets, Greenland and Antarctica, to global warming and assess the corresponding effects on global sea level rise. And we run computer model experiments to study how life on our planet, including vegetation, humans, mammals and plankton in the ocean, have changed in the past and how they will react to future warming and ocean acidification. Recently, we embarked on a new climate modeling project in which we aim to simulate the effects of increasing greenhouse gas concentrations on the climate system in the highest possible spatial resolution. This little video clip shows you some of the first results. Even though the video showing clouds looks like images taken from a weather satellite, it is simply the result of zeros and ones generated by our supercomputer in its attempt to solve the physical equations of the climate system. The computer model has not seen any actual satellite data, just mathematical equations. Using a global mesh of about 9 kilometer resolution, we begin to resolve individual cloud systems, and we can study the climate system more realistically than before. Unfortunately, I cannot present all the exciting projects in our center. I will therefore focus on only two representative studies. The first one deals with tropical cyclones, devastating weather events which are called hurricanes in the Atlantic and typhoons in the Western Pacific. A long-standing question is what will happen to these tropical cyclones in a warmer world? To address this question, we ran on our supercomputer Aleph a global climate model at 25 kilometer global resolution in the atmosphere and 4 to 10 kilometer in the ocean with different atmospheric CO2 concentrations. The simulations used the entire computer system for about 1 year. At 25 kilometer atmosphere resolution, the global model simulates tropical cyclones realistically, as you can see in this animation of our data, which zooms into the Japan-Korea region in summer. Tropical cyclones in this animation look like flying donuts, and the red color indicates the wind speed and the white shading the rainfall. After some further statistical analysis of about 1.8 petabytes of data, our simulations show that in response to CO2 doubling and quadrupling, the model simulates a decreased track density over almost the entire tropics and subtropics. And this pattern resembles the observed trend in tropical cyclone density, indicating that greenhouse warming may have already started to alter the observed tropical cyclone tracks and frequencies. We further investigated the physical mechanisms and concluded that the summertime headly circulation becomes weaker in future due to the accelerated atmospheric warming at an elevation of about 5 to 15 kilometers relative to the ground. Future reduction of rising motion in the tropical atmosphere will make it more difficult for tropical cyclones to develop, which explains the projected future suppression in tropical cyclone seeds. We further identified that although the total number of tropical cyclones is expected to decrease in future, developing events will have a much higher chance to intensify beyond Category 3 due to the higher humidity and energy levels in the atmosphere, resulting in 150% increases in intense landfalling tropical cyclones in the future. Moreover, we found that landfalling tropical cyclones will be associated with much more rainfall, showing how global warming intensifies the hydrological cycle. This is highly relevant information for policymakers and the general public, as decisions need to be made how to protect vulnerable shorelines and save human lives and livelihoods. Our second story takes us from the atmosphere to the underworld. South Korea has many caves, and our Paleo-climate team studies these caves, focusing in particular on stalagmites, which contain valuable information on the history of our planet. Scientifically as valuable as ice cores, stalagmites contain key information on climate processes such as changes in the extended monsoon systems or evidence for abrupt climate change. Interestingly, we have to go underground to reconstruct past changes in atmospheric circulation and surface climate. How do we do this? In our lab, we cut open stalagmites using a diamond wire saw. Stalagmites are made out of calcite, which contains, apart from a calcium ion, also oxygen and carbon atoms in different isotopic combinations. To study the isotopes in stalagmites, small calcium carbonate samples are drilled and analyzed in our different mass spectrometer systems, which identify the abundance of stable isotopes of oxygen and carbon. The relative abundance of these isotopes compared to a standard can then be translated into climate variables. As a result of this analysis, we can then reconstruct time series of past changes in temperature, rainfall, and elemental deposition inside the cave. The latter, which we measure with a laser ablation system, contains information on changes in the large-scale atmospheric circulation or soil processes. In collaboration with our colleague Professor Kyungnam Jo from Gangwon National University, we discovered a prominent abrupt climate anomaly in several stalagmites, which occurred 16,000 years ago during the last stages of the Ice Age. We call it the 16K event, and it's the most abrupt large-scale cooling event ever observed. According to our analysis, temperatures in the northern hemisphere cooled by 5 to 7 degrees Celsius in just 7 years. Our team is using computer models to test now the hypothesis that this event was triggered by a burst of a huge glacial meltwater lake into the North Atlantic and the corresponding changes in ocean circulation, sea ice, and the atmospheric circulation. Scientists in our center published their results in major scientific journals including Nature, Science, Nature Climate Change, and Science Advances. We issue about 5 press releases every year and communicate our main research findings to the general public. Furthermore, we engage with the general public by hosting regular outreach events, public lectures, climate training workshops, and open houses. We collaborate with science museums, share our perspective and science in newspapers and with TV and radio stations. The large amount of data from our supercomputer simulations are now accessible to everyone in the world for further analysis and exploration. If you have any questions regarding climate data or our research, please feel free to contact us. We look forward to hearing from you. With this, I would like to thank you for your attention.